The following message is best viewed on an oscilloscope.
So are we ready to go, Wojtek?
Go ahead, Steve.
Okay, excellent. Hello, everybody, and welcome to Universal Science. It's an absolute pleasure to have all of you join us this evening. This is actually our third edition of Universal Science. It's an event that we take advantage of a major conference, and we're at the ICHEP conference now, which was meant to be held in Prague, but which is being held virtually for everyone, for reasons everybody is aware of. But normally in these events, we are at a conference and we're bringing scientists together with the public who are nearby. In this case, we're all together because we're all in cyberspace. And so it's very exciting to have you all with us. We're going to have a chance to discuss the latest things going on in particle physics, the latest research. We're going to talk about diversity in international collaborations and about the future of our research and perhaps of our world. So my name's Stephen Goldfarb. I'm a particle physicist. I work for the University of Melbourne on the ATLAS experiment on the Large Hadron Collider, at CERN. And I'm excited to be here. I also happen to chair the International Particle Physics Outreach Group, who is one of our sponsors. I'm very happy that we're able to bring this to you this evening. I'm going to be co-hosting this with my friend and colleague, Marjana Lapka. Marjana?
Hello everyone. Thank you, Steve. So I'm Marzena Lapka, and I've been involved with education and outreach for the past 15 years, I think. I've been coordinating education and outreach activities at the CMS experiment at LHC, and currently I'm leading communication efforts at the Knowledge Transfer Group at CERN. So I'm going to take just 1 or maybe 2 minutes to explain you the agenda of the evening, so you can so here you can, so the evening will be split into 2 parts. So the first part we will have in the first part we will have 3 amazing talks, but by great speakers, and Steve is going to introduce you to each speaker before the talks. And so the first part will finish around 9:10, and this is when we will start answering your questions. And we have a fantastic panel with 3 amazing women who will answer your questions together with our speakers. And we will finish the program around 10 p.m. So I will now quickly explain you how to ask questions. So we are using Slido application for that. And so you can go to the link that I have on my slides, or you can go to the Universal Science website and click on the questions, and it will take you to this website. So you see the print screen, and here you have 2 options. Either you type your question or you vote for the question you like. So please go to Slido and ask your questions. I will be monitoring the questions, and we will start answering around 9 p.m. And last but not least, this This public event comes as part of ICHEP2020, and we would like to thank the following for their support: Charles University, Czech Technical University, Czech Academy of Science, International Particle Physics Outreach Group, CERN, CMS, and Atlas Experiments. So that's it for me, and now Steve is going to introduce you to the first speaker. I have to stop sharing. That's it.
You're very adept with this. We've been, I think everybody now is becoming adept with Zoom. So thank you very much, Marjana. Just to repeat, please ask your questions. We're here to answer questions. It's something that we really like to do because we like the work that we're doing. So you're going to hear 3 talks. We're going to save your questions until after the talks, as Marjana said, but we'll try to get to as many of them as we possibly can. So without further ado, let me introduce our first speaker, and that's Katarina Zetterberg. She's a senior lecturer at Lund University in Sweden. She completed her PhD on QCD physics, you guys all know that, strong interactions, on the Atlas experiment at the Large Hadron Collider in 2011 at Oxford University. Her interest in physics beyond the standard model and dark matter was developed during her postdoctoral research position at the University of Geneva, and now she continues her interest in this at Lund University. She is the principal investigator of the Dark Jets ERC starting grant. I mean, she's got some money, good job, and she's supported by the Swedish Research Council. Her group and colleagues are working on the challenges that a data-rich research environment presents. That means we have a lot of collisions to look at for discoveries of rare processes at Atlas. So, Katarina, she's going to present Shining a Light on Dark Matter. Go ahead, Katarina, take over.
I need 1 minute.
Okay. 1 minute, we can do songs and dances while you're, while you're coming on.
Now a presentation that you will be able to see. But the other thing that I've never done is that I've never tried to build the universe live with whipped cream. So how it works.
Yeah, show us how that works.
Then we'll take a technical break or something.
Okay.
Anyway, the first point is that how is the universe made? Well, we're making it inspired by physics cakes this time. I'll link a video later, but we'll do something simple. So we'll have a dark ice cafe. And what is a dark ice cafe? Well, we got a glass. Good. It's empty. The first thing that we want to put in is coffee. Actually, I'm using hot chocolate because it's a bit closer to dinner. So we're putting about, I don't know, 200 mils of this. It's going. Good. So this gives the dark energy of the universe. Now, the second thing that we need in the universe, we need about a third of that, half of that in dark matter. And that is going to be chocolate ice cream. This is going to take a minute. Here it is. Okay, there is some ice cream on my laptop now. That's great. It's about, I don't know, 100 grams of ice cream. All good. That's it. So we have the dark components of the universe. But now the third thing that we need is us. Is the matter that, is good. Is the matter that we're made of. And here we're actually using whipped cream. And this is going to be the tricky part. Because whipped cream is usually full of air, right? It's not just dense. And this is ordinary matter. The matter we're made of is mostly interstellar gas. So let's put some gas into our universe here. Okay, there's a tiny bit of matter here. It's about 5%. So we've made our ice cafe. It's probably going to taste good, but I'm not going to do the rest of the talk with some sort of mustache. So I'll leave it for later. So what have we built here? We built a universe that is made of 68% dark energy, 27% dark matter, and 5% ordinary matter. And now we're going to concentrate on the dark matter part. How do we know that it's actually there? So we need some evidence for dark matter. And the first piece of evidence comes from the early 19th century, actually, But we'll focus on something that Vera Rubin, a scientist that was studying with telescopes the universe in the 70s, that she observed. So the background that I have in this slide and the whole presentation is a galaxy. And a galaxy, this is the Milky Way, so it's there's a lot of stars, there's a lot of visible light. And what was expected if, for measuring the gases that rotate together with the galaxy, is that their velocity would decrease as a function of the distance from the center. So wherever there's less visible mass, then we have a decrease in the velocity. What Vera Rubin observed is that the velocity kept going up and kept being high. So that meant that there was something else that wasn't not just the visible matter. That's evidence number one. The second one is about gravitational lensing. And this is something that we've heard a lot about gravitational waves, and it does have to do with that. But let's try and see how it works. So the presence of something massive distorts space-time. And this is what also gravitational waves do. But whenever we try to observe objects behind a clump of invisible dark matter, we're doing that with the rays of light. We're doing that with our eyes. And these rays of light get bent. So the objects that are behind this invisible dark matter are not what we expect. So based on what our expectations and somehow interpolating between the lines that the light would have, like a bat, we can infer where the invisible dark matter is. So that's why gravitational lensing is important for dark matter, because we know that there's something invisible that distorts space-time. So let's see it in action. So this is the bullet cluster, and I hope that I can show the whole video. Yes, the bullet cluster is a cluster of galaxies, and you see here, if you point the telescope, you see the visible component, this is this pink, and also you see with gravitational lensing another component that is blue, that is dark matter. And together they make up the entire mass of this cluster of galaxies. How did that happen? Well, it took its name from a bullet, because it's essentially a bullet galaxy shot through the second galaxy and went through it, and then led to what we see now. And you see that there's a component in blue and a component in pink. The pink is visible, the blue is invisible. That's the dark matter. And you also notice that while the pink changed shape from the start, the blue didn't. And the blue is the dark matter. The dark matter does not really react with anything. It doesn't interact with anything. And if it interacts very, very little. So this is what we can see from this bullet cluster about dark matter. And then eventually in many years' time, it will go away as well. Anyway, now that we've seen the lensing picture of dark matter, let's go and try to remake the universe in a bit more of a refined fashion and with supercomputers with respect to what we've done so far with our ICHEP. We try to do galaxy simulations. This is something that physicists work on, simulating the universe, simulating matter, simulating collisions. That's something that we do a lot. So we can try and simulate how galaxies were formed. And we can decide what ingredients we want to put in. And we find out that we need dark matter as an ingredient because this is the only way in which the outcome of the simulation corresponds to our observations. And here I'll show you a short video about how galaxies form from a blob of ingredients. And these filaments are what constitutes the structure of our universe today. And without dark matter, these filaments wouldn't actually look like the way they do. Okay, now that we know that dark matter is there, let's try and hypothesize on what it is. And there's a number of hypotheses for dark matter, maybe too many. The only evidence we have for dark matter so far has to do with gravity, because we've seen gravitational lensing and we've added gravity in our simulations and so on. So we don't know exactly what dark matter is beyond that, but we want to narrow things down. So let's think about the case in which dark matter is a particle. And we often require that when we build models of dark matter, that this particle can make up the amount of dark matter left in the universe. So we want these particles to make up the 27% of relic density of dark matter that is still around today. But other than that, we can make dark matter small, we can make dark matter big, we can make dark matter more or less visible. But let's start with the distinction between light in terms of mass and heavy dark matter particle. So is dark matter a light particle? These are two possibilities that I find kind of funny, because one is called like a detergent. It's the axion dark matter. This is a really, really tiny particle that was hypothesized by a number of people. And one of them, Frank Wilczek, gave it the name axion because it cleans up a number of problems of the main theory of particle physics that we call the Standard Model. There's also another possibility. It's called the hidden photon or dark photon dark matter. And this is similar to the ordinary photon. So the photon is the particle that brings us light. And instead of being like a light bulb, it's a dark light bulb. It's much more elusive. And we don't know if it's stable or not. Like the photon could decay into something, and the dark photon could decay into something as well. So we look for a companion of the light that is the darkness. So if we go for a heavier particle, a more massive dark matter candidate is the so-called weakly interacting massive particle. It's a WIMP. It's a funny name because you think that the WIMP is something that is tiny and weak, but it's not. Actually, it's a large particle in our scales. It's about 10 to the 20 times more massive than the light candidates, more massive than the axion. And people are keen on this particular hypothesis for dark matter because theories that include the WIMPs could also solve other problems of the Standard Model. If you've heard of supersymmetry, it has room for a WIMP. Now we've talked about its mass, so we've explained the massive, but we've not explained the weakly interacting. So we assume that there is some connection between, it will interact somehow, because otherwise we can't really see it or make it. And we'll see why it's useful later. But these interactions are extremely weak. These kind of particles can be as elusive as neutrinos. And neutrinos, we know that they exist. We also know that they can't make up all the dark matter. And we know that for every second, 100 trillion neutrinos are passing through you. And none of the particles that you're made of notices. Maybe sometimes there will be a tiny interaction, but it's still really, really minute. And it's very difficult to find these interactions. But that is what dark matter physicists have to do. So let's see how to find dark matter. How do we want to discover it? And because we have so many different hypotheses for dark matter, we need different experiments to cast a broad net on different dark matter candidates. And maybe dark matter is not just one of them, maybe it's a mix of these. So what do we do? So for light dark matter, we either stare at it or radiate it. Let's stare at some dark matter. And this is what axion searches and axion experiments do. This is just one kind, there are many more. But under the hypothesis that axions could be concentrated in the core of the sun, then you can point a telescope to the sun, use a magnetic field to turn these axions, these particles that we can't see, into particles that we can see, photons. Then we take pictures of them with a very advanced camera. And this is the way that we can make the dark sun visible. If we're instead talking about the dark photons, this is only one kind. Again, there's so many more experiments. I don't have time to go through all of them. We know that whenever we throw an electron into ordinary matter, then sometimes we generate a photon. So maybe we could also generate dark photons in the same way. So the best way to do it is always smash things into other things. That's what we like doing a lot. So we can smash a large number of electrons into a dense target. And then if we have a dark photon that is going out, or a normal photon that is going out of the electron, then the electron will deviate a little bit. So we want to check whether there are any off-course electrons after the target that don't have a visible photon that corresponds to this deviation. Because this means that there is a dark photon and it may have decayed into invisible particles, so we don't see anything. And this is what the light dark matter experiment LDMX does. So this is for light dark matter, just a taster. And what do we do for heavy dark matter, for the WIMPs? Well, you can make it because we could produce dark matter at the Large Hadron Collider. So at the Large Hadron Collider, we collide ordinary matter particles at very high energies. And because E, the energy, equals mc squared, so you can convert energy into mass and vice versa, then you can create bigger particles. You can create dark matter particles. And then the other thing that you want to do is measure what escaped these giant detectors. And this is not something that we can do in this short period of time, but if you want, we can play with it during the question and answers. And so I will show you a very, very short video that you probably have seen. You might even have been inside an experiment today, inside the ATLAS experiment. This is how the collisions at the LHC could produce dark matter and how we could see them. Okay, so we've tried to make dark matter, let's try to shake something with dark matter, and this is what we call direct detection of dark matter, where a dark matter particle hits a particle of ordinary matter, for example, in your detector, and ordinary matter doesn't like it very much, and it's slightly perturbed by this kick. What is left to do is to detect this kick. So you need to see a tiny movement of the ordinary matter particle. And you can do that with either giant or very sensitive underground detectors. So this is an example in the figure of an experiment that is placed under the Gran Sasso. So it's one of the highest mountains that you have in Italy. And you want to have this experiment very, very low on the ground so that there's nothing else but dark matter and neutrinos that make it there. So we have made it, shaken it, and now let's break it. And breaking it is the method that is used in dark matter and direct detection. It's not us breaking it, it's dark matter colliding with other dark matter particles in space. And they can transform into ordinary particles in the opposite way as we were making it at the LHC. And what we detect is changes in the fluxes of ordinary particles. So as long as we know how many ordinary particles we expect, then we can see if there's anything more than that. And we do that using telescopes, either in space or on Earth, or even in the deep underground ice of the South Pole. And this is a picture of the IceCube collaboration. The picture is not to scale, so the building, the experimental building on the top is tiny compared to what is all this instrumentation in the ice. It's, I think, 100 times the Eiffel Tower, that instrumentation. It's huge. And this is, you need huge detectors because dark matter interacts very, very little with anything. And so in order to be able to catch something, we absolutely need a large volume. All right, so I've shown you what we can do and what next. What next is that we are looking for dark matter and we've not found it yet. But at this conference, we've seen a lot of experiments that have some interesting results that need confirmation. So we need a lot of different experiments again. And we keep on looking because we know that dark matter is there. There is no doubt that there is something missing in the ice cafe of the universe. And we miss ice cream. No one wants to miss ice cream. So what do we need here for going forward? We need more theory ideas because we don't want to just look under a spotlight that we know. And this is something that Suchita Kulkarni is an expert in, so you can ask her questions in the panel. And then there's more advanced experiments, and here we have, we're lucky to have two people from the CMS experiment, Jennifer and Patricia. And we can make bigger detectors and analyze more data with also new analysis techniques, including artificial intelligence, that is one of the expertise of Jennifer. We can also use new materials for new detectors, so you name it, the graphene, nanotubes, anything that could react interestingly with dark matter. And we can also use gravitational wave detectors to say something about dark matter. And then last but not least, more collaboration is needed and planned among people that want to discover dark matter. This is a huge community. And here I'm pointing to John and Kate that are the experts in turning what we know into knowledge of the unknown. So this is, I hope I gave you a bit of a taster of the universe. Now I'm going to have my ice cafe. So thank you very much for listening and to the host for inviting me.
Thank you very much, Katarina. That was fascinating. It was fantastic. And I'm really envious that you now have the universe there next to you. I wish I don't have quite the same here. I can only, first I want to remind everybody that we're going to have questions answered for you at the very end of all of our talks. So please, if you're watching on YouTube, down below the YouTube window, you'll see that there's a link to a place called sli.do, okay, sli.do. That's where you can ask your questions. So go there and ask your questions, specific ones for Katarina or general ones. Please go ahead and ask them. I have one simple one I would ask now. I can only assume that with this brilliant contribution to astronomy and to physics, that Vera Rubin must have received a Nobel Prize. Didn't she?
Oh.
Let's, maybe that leads, well, go ahead, Katarina.
She had very nice words about doing science for the science rather than for the prize.
Yes.
Yeah, thank you.
Yeah, we do science for the science. Recognition would be nice though. And that maybe leads in to the next discussion, which is going to be Kate Shaw is going to talk to us a bit about diversity and a little bit of our lack thereof. So thank you again, Katarina. Our next speaker will be Kate Shaw. And Kate is an experimental particle physicist at the University of Sussex in the UK. She's working also on the ATLAS experiment on the Large Hadron Collider. She's also a staff scientist at the Abdus Salam International Center for Theoretical Physics, also known as ICTP, in Italy, which is a UNESCO institute, very interesting place. She completed her PhD in 2010 on the commissioning of part of our inner detector system, the ATLAS semiconductor tracker, and vertex reconstruction with the tracker. Her work currently focuses on searching for new physics through precision measurements of the top quark. There's a lot of ways we look for new physics. One of them is to measure things as precisely as possible and try to figure out where that deviates. She co-coordinates the ATLAS Open Data project, so you can actually play with our real data, and is one of the ATLAS diversity and inclusion contacts. Kate founded and co-coordinates the ICTP Physics Without Frontiers program, which works to train physics students in developing nations, for which she won the 2015 European Physical Society's Outreach Prize. And she works to support diversity in physics worldwide. So Kate is going to present us with strengthening physics through diversity. Kate?
Hi, thank you so much for that very nice introduction, Steve. So hello and good evening, everybody. So I'm afraid I'm not going to make any nice copies of the universe for you today, but I'm going to be talking to you about strengthening physics through diversity. Okay, so I think as Katarina actually briefly introduced, at the Large Hadron Collider, we collide these protons millions of times every second in the center of some of our main experiments. And when we do these collisions, we create and we reconstruct and we study some of the most fundamental particles of our universe. And to do this, we're using some of the most complex machines in the world. We're constantly striving to answer new problems, to upgrade and improve our detectors, our technology, and our algorithms so that we can really see even further into nature's mysteries. So how do we achieve this? So one of the key things we need is, of course, physicists, and we need a lot of them. So the LHC experiments have literally thousands of collaborators, physicists, engineers, and technicians from all over the world. And we work together around the clock to make measurements such as those that we've been seeing this week at ICHEP. So just in our ATLAS collaboration, so ATLAS is one of the 4 main experiments on the Large Hadron Collider. Just in this collaboration, we have over 5,500 members, and these come from 103 different nations. This really means that in our experiment, we can get the best talent and become a world-class experiment. So diversity, having people from so many different backgrounds, cultures, and nationalities really is key to the success of our physics. So let's have a little look about why that is. So imagine we have a group of 100 people. If we want to select 10 of these people to be in our physics collaboration, if we chose those people that all had, say, the same gender or ethnicity, or they were from the same nationality, or somehow had a similar background, you'd end up with a group of 10 people that might all have a very similar approach to solving a problem. So what we mean by diversity in science is we need to be able to solve kind of complex problems that no one's seen before, be able to do science that we haven't been able to understand before. And so when you have a group of people that have different backgrounds, different cultures, different experiences, they bring new experiences and perspectives to solving problems. It brings innovation, and the mix of the different people and perspectives can ignite creativity. And of course, we want to draw from the full pool of people. If we're only drawing from a group of 10, we're not looking at the full talent. So we need to make sure in physics, to get the very top talent, we need to have everybody included. So diversity is key, but collaboration is really at the heart of what we do and our achievement in physics. We have to collaborate in order to build these great machines and do these types of physics. So here you can see one of our papers, which hit, it set new records. So this is the Higgs boson discovery paper, an update of it. And this hit a record because we had more collaborators, more authors on this paper than any other paper before. So over 5,000 people. This was an authorship on the paper, and this is a mix of ATLAS experiment and CMS experiment members. So this was a really incredible feat to find the Higgs boson, a very elusive, very rare particle. So how do we do this kind of science with ATLAS and CMS? So they work in competition with each other. They're two different experiments. They have different collaborators. Both of the detectors are designed independently, the reconstruction algorithms done independently, and of course the analysis done independently. And of course both experiments, ATLAS and CMS, they're kind of in friendly competition. They both want to get the most precise measurement. So of course this means it's going to drive innovation again to try and look at their calibration, their reconstruction to really get these precise values. But when they have finished, they then come to collaborate. We're all after the same goal. We want to get the Higgs boson. And although the friendly competition helps drive the innovation, it's the collaboration. So by combining the data from both ATLAS and CMS, this allowed us to have an extremely precise value of the measurement of the Higgs boson. So to do this sort of science that we do at CERN and Fermilab and other international laboratories all over the world, these ambitious projects, they need international cooperation. So CERN was born in 1954. So this was only a few years after the Second World War. Science, I mean, a lot of the scientists had left Europe. Europe wasn't really still a world-class centre of science. So 13 European states that not so recently ago were at a very bloody war with each other managed to come together through international collaboration to build this centre of research, fundamental research in physics, which we now know as CERN. So CERN today has 23 different member states and many, many countries from around the world participate, which you can see from that map. So it's a real force for good to have this centre of science where, some of the countries that participate, they may not get on with each other. There may be some countries that are on experiments that may still be at war with each other or economical battles. But science builds this bridge between countries so that they can come together and work towards a common goal. So the International Centre of Theoretical Physics, this is in Trieste, Italy, where I also work. So if you know where Trieste is, just on the map on the left, you can see it's in the northeast of the country. This used to be on where the Iron Curtain used to lie. So this was about 10 years after CERN was created. ISTP was created during this Cold War era to be kind of a line of communication, a place where scientists from both east and west sides could come together to collaborate. And it worked then, and it's very much working now to support those in developing countries, to be a centre of international collaboration. So again, building bridges between east and west, and now between the global north and between the global south, to bring scientists together to collaborate. Okay, so is physics diverse? I've just been talking a lot about our wonderful collaborations and how international we are. However, we live in an unequal world. Internationally, the opportunities you're going to have to do physics research depends very much on your country. So many countries, mostly that come from lower economic environments, they're going to lack resources, and the universities massively lack investments. And so many scientists, especially from developing countries, they simply do not have the same access to funding and governmental support as other scientists. And of course, many students and young people, they lack exposure to fundamental research and research opportunities, they lack access and opportunities to go on to further study. And again, this costs us valuable scientists. So on the right, you can see one of my friends and colleagues, Dr. Wafa Qatar. So she's a theoretical physicist at Birzeit University in the Palestinian territories. And so Wafa and very many of her colleagues, they really don't get given time to do research. They don't get funding from the government to buy out their time to be able to do the research. A lot of what they do comes from work in their own time. They're so passionate about their physics that they do it even though it's outside of their working hours. They don't get access to research grants that other scientists can apply for. And also it means they can't attend international conferences. So international conferences are super important for physicists. It's where we get to present our latest findings, and you meet many other people and you get to collaborate and make new collaborations. But unfortunately, many scientists lack these things. And so there's a big inequality between scientists from one country to another. So this is a picture of a physics school with students from Kabul University in Afghanistan, which we've been running under the ISTP Physics Without Frontiers program. So all the students you can see, these are all undergraduate physics students. They're super passionate about physics. Of course, they chose physics out of every other topic you could study. And you never know, there could be an Einstein or a Marie Curie in the audience there. However, the students there are very isolated. They don't have a master's program in Afghanistan, and they don't get access to a lot of opportunities that other countries do get access to. So since there's no possibility to do a master's degree, this is often the end of the line for them. And as I say, some of them could be these top scientists, and we're losing out in science because they don't have these opportunities. To get funded masters abroad is super difficult. And so we end up losing these students. So unfortunately, internationally, it does very much depend on which country you're from to know if you're going to have the success of becoming a physicist. But ISTP and CERN are doing a lot of work, and other institutions and organizations too. So ISTP has a joint mission actually to do excellent science and research, and also to support young people into physics, and to run various programs and conferences and funding to support physics in developing countries. And CERN also has wonderful programs to support students and scientists from non-member states to join. So this is great work. We really want to encourage more of this. Okay, so I just talked about diversity internationally, but what about national? So I mean, inside of our own countries. So again, we're not as diverse as we would like. Within our physics communities, we can say there's many groups that are underrepresented. And as we said before, we have underrepresented groups. We are not pulling from the full pool of talent that we should be. And this can be aspects such as people's gender, sexuality, ethnicity, or social economic background. So this is an issue that I think many countries, many universities are really thinking about now, because it's become very clear that we need diversity in science and physics. But the issue is you've really got to recognise what barriers, what issues are affecting different groups, because if you're privileged enough to get to the top quite easily, it's not obvious to know what kind of barriers other people face. So by talking and learning, we're slowly being able to work with universities and with institutions and governments to help diversify nationally our physics. And this involves a lot of outreach initiatives, working with young people, and of course role models play a really, really key part in here, and supporting new initiatives. So I'm just going to finish by just showing one initiative we worked on in South Africa to address the lack of women in physics. So this was working with Sahal Yaqub, with the Organisation of Women in Physics in South Africa, and the University of Cape Town and ISTP. So it was a simple communication project. We found 7 physicists, female physicists from all over different parts of South Africa, and in different stages in their career as much as we could. And we wanted to make these 7 posters. And so each poster has just a simple picture of the person surrounded by something to do with their research and an inspirational quote. And so these posters were created, and we displayed them in high schools throughout South Africa and at science events. So the reason behind this is that role models, as we know, are really important to help people envision themselves to be in a certain role. If you only see one type of person in a certain role, you could never think that would be something for someone like yourself. So role models are super important. And then imagery really works. We know this because from advertising, companies spend a lot of money on advertising. So by having these posters just simply on the wall, we really hoped would just affect high school girls and high school boys about what a scientist looks like and what kind of thing that they do. We wanted to change people's general opinion of a physicist. So I just wanted to show you a couple of quotes, because I think I haven't got time to show you all of them, but they're really nice quotes. And the idea was that they would somehow maybe resonate with different young people. So on the left, we have Helen, and she says, "My mother is my greatest support. She always says, if you have education, you can equip yourself for life." So this was great. She was very motivated by her family. And on the right here, we have Riona. And so she says, "My grandfather used to take me to the library every week. And I always made sure that at least one of the books I took was a science book." And she talked a lot about her inspiration from reading when she was younger. And so, yeah, we really think that doing these kind of communication projects, accessing the young, giving good role models is a good way to help at the bottom to help diversify physics. Okay, so thanks very much for listening. Thanks very much to the host. Hopefully I've discussed a bit about why diversity, of course, makes physics stronger. It's something that is essential within our collaborative environment. We recognise there's things we still need to work on, and I hope we're going to continue working on these things. But we're very proud of our international and our very diverse community. Thanks.
Thank you, Kate. Thank you for that very informative talk. It's really important. The work that Kate's doing, you can see its impact. We can see students, well, back in the day when we used to go to CERN and used to hang out in the CERN cafeteria, if everybody can remember that, we would run into these students and now physicists who Kate helped to hold the interest of and get to go into the field. And it's fantastic to see that. And some of them bring back what they've learned back to their countries. And she's planted some seeds there that we hope are going to grow. And in addition, I completely underline what she said about collaborations. It's the greatest experience in the world to work on these international collaborations and to meet people from absolutely everywhere. That's the only way that we can do physics, because you need a lot of different points of view, a lot of different methods and ideas to come up with our measurements and what we do. So thank you. We are going to come to our last speaker now. And I just want to remind all of you one more time, you can ask questions. I see there are some nice questions coming up on Slido. Please go ahead, ask more questions. Also note that you can check out the questions that exist there on the list, and you can upvote the ones that you like. That's a good idea. You can see the link either if you're on the Universal Science page, it's at the top, but you're probably on YouTube. If you are, it's just down below. You can see the link down there under the video. So let's bring up our last speaker. That's John Butterworth. He is a physics professor from the University College London, and he also works on the ATLAS experiment at the Large Hadron Collider. John obtained his doctorate from Oxford on the Zeus experiment at Daisy in Hamburg, and yes, I remember that, where he was later the physics coordinator of the experiment, and he held an Alexander von Humboldt Fellowship. John won the Chadwick Medal. That's a very prestigious medal, prize of the Institute of Physics in 2013 for his pioneering experimental and phenomenological work in high energy particle physics, especially in the understanding of hadronic jets. These are these big jets of particles that come out when we have collisions. He was the UK delegate to the European Strategy for Particle Physics Updates in 2013 and just recently in 2020. He's going to tell us a little bit about that. The strategy helps to blueprint our path forward. It's a lot of very bright people thinking about what are the next steps we need to take for the field of particle physics. And so we'll learn a little bit about that. John also writes regularly for the general public. It's fantastic, his writing. His most recent book, which is called A Map of the Invisible, was published by Penguin in 2017. I highly suggest all of his books. They're fascinating and fun to read. John is now going to present particle physics for the future. John?
Thanks a lot, Steve. I wish I hadn't told you all that stuff now. Okay, so I'm just get the slides up. and move to full screen. Okay, yeah, so the final one of these little triptych of talks is particle physics for the future. And by that, I mean, what may the future hold for particle physics, but also what maybe can particle physics offer for the future. And if you're going to start a talk like that, then probably the first question you want to answer is why keep doing particle physics? We're assuming kind of that it's going to continue into the future. And that's a good question, actually. It's a question that we should keep asking ourselves as particle physicists, and it's a question society has every right to ask of us as well, since we draw down resources from society to do what we do. And it can sometimes seem hard to answer. I mean, sometimes particle physics can seem to be just about building bigger and bigger and more expensive machines to chase down slippery theories that maybe very few people understand, or devising ever more abstruse and intricate ways to measure arcane things more precisely. And I think you can make a case. I mean, there's an element of truth in that. I hope I can persuade you there's more to it than that. But I think you can make a case for continuing with particle physics, even if that was the whole story for you, because these challenges drive a lot of people. You've just been hearing from the previous two speakers how that works. They drive people against challenges that we test ourselves against, and human beings, I think, as a society and as individuals, we need sometimes to test ourselves against difficulties. And we have an unfortunate tendency, I think, if there aren't objective difficulties out there to test ourselves against, we can create them. And so even in a difficult situation like we're in now, I think having challenges to address ourselves toward is something that has objective value, and those challenges drive and exploit technological developments, and they also drive and exploit international cooperation, as you've been hearing from Kate there. So I think even when we have challenges like the pandemic that's stopping us being in Prague now, like the climate emergency that's developing, like the numerous political challenges around the world, there's still value in the activity of particle physics, so long as someone is interested in these abstruse questions, as long as the people who do it are interested in them. However, I think obviously there's more to the story than that. That is not the story. We're not just chasing down strange theories that no one understands. Particle physics is about, and always been about, exploration. It's about human beings trying to understand how the universe works and what it's made of. What are the underlying principles that govern the place we live? Now, actually, a lot of blue sky science, a lot of fundamental science actually addresses those questions. Particle physics is not the only way of doing that, but our speciality is the question of what are the fundamental players, what are the fundamental constituents and forces of nature that underlie all this. And that's the common goal. That's what actually brings the wider benefits. It's this vision, this idea of striving to explore the world we live in to the best of our abilities. And without that vision, if you like, then all the societal and economic and technological benefits that flow from the subject would dry up as well. So we haven't been idle, of course. We have a sort of answer to that question. What are the fundamental constituents of nature? And it's sort of summarized on this slide. There are the quarks up there in the top left, sorry. There are the electrons. Between them, those are the matter particles. If you put those together in the right way, you can build the whole periodic table and therefore all the matter that we see around us. And the things that put them together in the right way basically are the forces, which are there on the right in the purple boxes. The photon, which carries the electromagnetic force, the gluon, which binds the quarks together inside the atomic nucleus, and then the W and the Z that carry the weak nuclear force, and behind it, the Higgs boson, making the whole thing hang together. That's great. It's, there's a lot of physics, there's a lot of science, there's a lot of phenomenology in general expressed in that slide somehow. But I'm not very happy with it myself. It looks a little bit to me like one of those books, when the World Cup's on or something, and you have a sticker book and you've got to fill in the stickers, and you've got to get the footballers and make sure any blank spaces you have to get filled in. You have to swap them with your friends at school, whatever, until you've got the album complete. And it kind of looks like, we've completed that now. We've got a Higgs boson. That's the last one filled in on there. It's not really the way I think of what we're doing in particle physics. The way I think of what we're doing is much better expressed in this slide, which is a kind of geographical representation of the standard model of particle physics. So all the same things are on this map. You've got the leptons, you've got the quarks, all building the matter we know, the atoms and the hadrons that are inside the atomic nuclei. You've got the forces interacting between them. In this conceit, for instance, the aeroplanes are the weak force and the trains are the strong force and so on. And what we're doing on this map is exploring the territory, really. So we're discovering new lands, and when we discover them, we're exploring them and seeing what's actually happening there. And one of the features of the way this map is presented is that the action in high energy physics is all going on in the east, actually. So the map sort of has low energy everyday physics on the west and high energy physics on the east. As you go further and further east, which is where the Large Hadron Collider and the science I work on is probing, then you're going to higher energies, but you're also going to smaller and smaller detail. You're looking at higher and higher resolution, you're probing deeper and deeper into the heart of matter. And that's really not a trivial connection there. The fact that high energy means small stuff. It seems kind of paradoxical that the biggest experiments in the world are often geared at looking for the smallest things we know of. And I've got a little video now that I just want to show, which is super high tech. It's just a ripple tank, which illustrates that point. So I want you to imagine that when you see this, that you're going to see a bunch of ripples, waves rippling across a tank, and that's a beam of particles. And my experiment, the ATLAS experiment, is on the right there at the end. It's a screen on the right. So by looking at those waves arriving at my detector, I can tell what's in the tank. And at the moment it's empty. The waves are arriving undisturbed. There's nothing there, okay? Now, if someone comes and puts a blob into the tank, now you see the waves are disturbed. There's a shadow arriving at my detector. If I had some smart computers, I could certainly tell there's something in the tank, could probably tell you roughly how big it was, maybe even what shape it was. Good experiment. Next experiment. This one doesn't work. You see the waves reform around the blob, and that's because the wavelength of the waves is too big to resolve that blob. There's nothing arriving at the detector that we could see. What they're doing now is increasing the energy, which increases the frequency, which shrinks the wavelength, and now you see there's a shadow formed again. So now the ATLAS detector knows that blob's there, whereas with the low energy beam, it didn't know. With the high frequency, high energy, and therefore short wavelength beam, it knew. So thanks to Herbie and Michael and my mates in Bonn who did that. But in a nutshell, that's kind of particle physics for you. We can see, for instance, we see with optical light with our eyes, we can see things a few hundred nanometers in detail. That's quite good. But if we want to see smaller stuff, we have to go to higher energy, say X-rays, which are like just photons of light, but with a higher energy, therefore a shorter wavelength, therefore better resolution. And if you like, you can view the Large Hadron Collider as the end of that chain. It's the best microscope we've ever built. It goes to the highest energies, so it has the highest frequency, so the shortest wavelength. Therefore, it can probe deeper into the heart of matter than anything we've ever done before. So that's what we're doing. That's our vessel that's guiding us eastward on this map. And what you see now, you'll notice that the east coast of that island down there, Bosonia, is a bit fuzzy. And this is the situation before we had the Large Hadron Collider, before we began with the Large Hadron Collider. And we knew there was something, we had theoretical and experimental reasons for knowing there was something interesting to be discovered around the east coast there. And I've got this is probably my most technical slide, but this is the experimental and theoretical evidence that we knew something was going on in Bosonia. So what you're looking at there is actually a plot from the Zeus experiment that Steve mentioned in the introduction in Hamburg. And what we were doing is smashing electrons into protons and breaking the proton into pieces. You can see that over here on the right. And sometimes the electron will bounce off and remain an electron. It will swap a photon with the proton. So it's an electromagnetic interaction. And that's the blue line. So the vertical axis is just basically how often the thing happens. And the horizontal axis is the energy. So you see the blue line there, the data points agreeing very well with the theory. We understand what's going on. The red line is when a different process happens. It's when the electron actually transmogrifies into a neutrino, and to do that, it swaps a W boson, which is a carrier of the weak force. And you see that's much less likely to happen at low energies. The red line is very, very far below the blue line. That's why it's called the weak force. It's very weak. It doesn't really happen very often. But as you go up in energy, a key thing happens. Those lines come together. And at some level, at some energy, which corresponds to roughly 100 times the mass of the proton, those forces are in a sense unified. physics has qualitatively changed at that energy scale. That's the scale, we call it the electroweak symmetry breaking scale. We actually knew quite a lot about that. We have a theory that says that actually this happens because the W boson has mass and the photon doesn't. But that kind of kicks the can down the road and says, where did the mass come from then? And the theory underlying this then, of course, said that actually the answers to these questions and why these forces unify, to get those answers, you have to go there. You have to go to that energy. In fact, you have to go well above it and understand it. And if the theory was right, then you will find a Higgs boson there. So that's what the LHC did. It got us over this ridge of mountains that I've drawn on there called the electroweak symmetry breaking scale. It gave us access to the east coast of Bosonia, and we've been exploring that ever since. Not only are we exploring that new territory that the LHC has given us access to, we're sailing eastward still. In a little boat is the high luminosities of the Large Hadron Collider sailing into the unknown ocean now, off the map, which is quite dramatic. We don't have so many clues now from the theorists as to what might be out there. What I like to think of as doing actually is sitting in a bar on the dockside and on the east coast of Bosonia, chatting with the theorists, and they're telling us all kinds of crazy stories. And you already heard about dark matter from Katarina early on, that maybe supersymmetry's out there. Gravity hasn't even featured on our map so far. Maybe there's some answers to how it can be brought into the same picture out there. Who knows? But the key point is we know, and you've heard some of the evidence already in the first talk, we know there's more land out there. We know there's something going on. We know it isn't just this archipelago of islands and that's it, but we don't know what. And the only way to find out is to go look and build a bigger boat. So the LHC is heading out there already. It will have a limited range. There are already discussions about building a future circular collider. You see the path of the hypothetical future circular collider drawn over Geneva here. With the Large Hadron Collider not looking quite as large as it does there on the Swiss-French border, just to the west of Lake Geneva. This now has a design study for this has been kicked off by the European strategy, which Steve mentioned and which I'll come back to shortly. But this is obviously a huge mega project to do it, and the point is to get us further out into that unknown Eastern Ocean. It's also actually, I should say, not just about the eastward exploration. There are bits of this map that aren't so well known elsewhere as well, and this bit that's highlighted here is the kind of wilderness where the neutrinos live. And we thought for a long time, it's not very well explored. We thought for a long time that neutrinos had no mass. We now know that's not true. In fact, the mass they do have may be intimately connected to the reasons why the universe is made predominantly of matter and not 50-50 matter and antimatter, which naively the laws of physics would suggest the Big Bang should have made equal amounts of both of them. So this is also another area well worth exploring, and there are big projects doing that. There's what you see here is DUNE, the Deep Underground Neutrino Experiment, which is under construction to fire a beam of neutrinos from Fermilab near Chicago to South Dakota. And there's another experiment in Japan, the Hyperkamiokande detector will receive a neutrino beam from the J-Park facility. Both of these are designed to explore the kind of really poorly known wilderness, really, of the neutrino region of the map. What they have in common with the FCC that I showed you earlier is that they are big projects. They're not the kind of project that any one country is going to do on its own. They require long-term commitment of people's careers and of resources. And so you do not just invent one overnight and decide to go ahead. You consult very widely and you do a lot of studies before you do it, before you decide to commit to one of these things. We just completed a process like that, again, that Steve mentioned in Europe, but with global participation from all around the world to develop a strategy. And that's the decision that kicked off this design study for the Future Circular Collider that I showed you. The slide I'm showing you here is from a big public meeting in Granada last year. We also had a less public meeting in Bad Honnef in Germany in January, just before everyone was locked down, to finalize the strategy, and it was announced in June as to what the priorities will be. And they include that Future Circular Collider design study. They include pushing the high luminosities of the LHC as far eastward on that map as we can. And they also include the neutrino experiments that I mentioned there, as well as many smaller scale activities. And there's a similar process going on in the United States now, called SNOWMAS. I actually went to one of these when it was actually in SNOWMAS, which is great because it was a ski resort, although it was in the summer, so there was no skiing. Now it's entirely virtual, and it's also, again, not just the United States. It has involvement from all around the world, including from Europe, but also everywhere else in the world as well, and is undergoing a similar process so that the US community can, in the context of the global community, decide what its priorities are for the next few years of particle physics. And it's really important, given the scale of these projects, that these are global, that they're sustainable, that we're using resources wisely, and we're limiting our negative impacts on things, and we're maximizing our positive impacts on things. And also that we're not just doing more of the same, only bigger, that we're continually pushing technology challenges to do more with less all the time, or ideally more with the same, but nevertheless, to get us further east with smarter technologies. These are big collaborations, so it requires a lot of consultation and discussion to pull that together. So that's kind of where we are. As I say, I think we're not really just sitting on the shoreline here. We are already sailing eastward. There may be surprises that show up in the next few years. There may not. We're in a rather different situation than we were when we were proposing to build the Large Hadron Collider, I have to say, because then we had this fuzzy outline of the island. We had good evidence that there was really something within reach that we could discover. Now, in fact, the situation could be bleaker. The standard model could be isolated. We know there are things out there. We know that dark matter needs a solution. We know that the fact that the universe is not made of 50-50 matter and antimatter is not understood within our theory. We know that gravity is not even really understood within our theory. And there's more issues to be dealt with. So we know that this little archipelago we've explored so far is not the whole story. But honestly, we don't know what's out there. All we know for sure is that if we don't look, we'll never know. Thanks.
Thank you very much, John. That's fascinating. I love your map there, and I hope that we're going to get to travel east some more in the coming years, coming decades. I think it's going to take, but who knows? It will give us a taste of something other than whipped cream, I think is the whole goal of this.
Maybe that too, though. Who knows?
I mean, I like whipped cream and all, but you know, it's time. Maybe it's time to move on to ice cream and to hot chocolate as well. So it looks like we've gotten quite a few questions coming in, and people are upvoting them. I'll let them continue to do that. And in the meantime, what I would like to do is I'm going to introduce, we have some panelists who have joined us, and they're wonderful people. I'm very glad to have been introduced to them, because there's not people that I have actually met yet, even though pretty much all of us are working in the same field in the same place, but we don't all get to meet each other, especially these days where we're all working from home. So I'm going to introduce you to our panelists. And then we're going to go to questions, and the speakers and the panelists will then try to answer as many questions as we can. Okay, so let me first just introduce Suchita Kulkarni. Suchita is a theoretical physicist working on the topic of dark matter with a close connection with experimental particle physics. So she's the loner here. She's the only theorist. Be kind to her. We usually aren't. So she is also an associate theorist with the CMS experiment. She completed her PhD from the University of Bonn in 2011 and is currently an Elise Richter Fellow at the Austrian Academy of Sciences in Vienna. Suchita will soon embark on establishing her own group. That's a big step forward on dark matter phenomenology at the University of Graz, and is supported by the Austrian Science Fund. Her hopes are to unravel the mystery of dark matter with the help of the results of the experiment, some people like Katarina. So Suchita, welcome. Can you perhaps tell us a little bit about yourself and about your work?
Right, so yes, as you said, the big physics question that I'm interested in is how do I get to the ice cream that Katarina was talking about? I like very much ice cream part of the story, and I want to know what the ice cream of the universe is made of, right? And to do that, I live somewhere on the boundary of where the ice cream meets the coffee. So we have the theories of dark matter, which can be wild, as John was saying in his talk, could be all sorts of beasts there. And this this theory, when it meets to the known constituents, the standard model, we do the experiments and it tells us something. The big question is, what is it that it tells us about the nature of dark matter? And given that knowledge, how can we proceed further? So that's basically the kind of interplay that I'm interested in, right? And if we talk about this interplay, one of the other things that I like to do then is to take what I understand and tell it to everybody. Because of course, I'm happy about what I understand and I would do everybody else to know about it. And from that point of view, I sort of like to talk to people a lot. And one of the things that increasingly over the years I have come across in terms of diversity and in terms of public outreach in science is it is not entirely trivial to make it accessible for a physically challenged or disabled community of any sort. So now I'm sort of also becoming increasingly interested as to how do you overstep the barrier of accessibility in science and go on to making it more far and wider reaching. So that's all from my side.
Okay, thank you. Maybe you can just tell us a little bit of your background, where you've come from, and what brought you into particle physics.
Right. So I'm from India, from a suburb near Mumbai, actually. And what brought me into science was actually my very first sky observation session. I went for a sky observation. There was a telescope. They put Saturn through the telescope. I put my eye onto it and I lost it. And that was the time when I said, if the universe looks as beautiful as it is, then I want to know what makes it tick. And that's basically where the whole story started. And I'm very glad to be where I am today.
Very good. Very good. Thank you. Okay, well, we're going to hear more from you because theorists always end up answering a lot of questions in these events, just fair warning. But I want to move on. We have another panelist who's joining us from across the ocean. Her name is Patricia Rebelo Teles, and she's a researcher and lecturer at the University of the State of Rio de Janeiro in Brazil. She got her undergraduate degree in mathematics in 1991. But after all, it took a long family break before she completed her PhD in phenomenology of particle physics in 2012. I just want to point out that's unusual. It's not easy to get back into a field after a long break like that, which she did in Sao Paulo. In 2013, she moved to experimental particle physics in her postdoctoral research, joining the CMS collaboration at the Brazilian Center for Physics Research, and subsequently spent a few years at CERN, where she joined the Physics Performance and Dataset Project while also guiding high school students during local and virtual visits in the CMS cavern. I hope some of you had a chance earlier in the day to see the virtual visit from Atlas. A lot of the experiments do virtual visits now. Her work focuses on searching for new physics through anomalous signal detection using deep learning techniques. In Brazil, she is involved in scientific outreach with IPOG Brazil, yay IPOG, and in social projects to support diversity and high school students from poor communities, in particular girls in science. Recently, she's joined the American Physical Society Inclusion, Diversity, and Equity Alliance, called APS IDEA. So Patricia, welcome. Please tell us a little bit about yourself, your background, and your work.
Yes, thank you, Steve, for the nice introduction. Yeah, so you did already, okay, so you said everything about me. I don't think I have much more to say. But yes, it's very interesting because, well, as you know, so from Steve, so I work in TMS. You can see my baby here behind me, okay? And yes, as Steve said, I have started quite late, my master and my doctor, my PhD, because of many reasons. But so this sort of, so this way I could get more experience dealing with people. So the maturity, you see, increase, and so it's easier to deal with people when you are maybe older, right? But so in CMS, so I am very, very supportive of Katie talk, because I see the same here in Brazil. You know, Brazil is, so our history is based on, unfortunately, on slavery. And so we are an unequal country, right? Huge, and in all senses, yeah, the inequality. And so, so we try here. And CMS, when I joined CMS, so I did my PhD in phenomenology. And when I joined CMS, so I have found an environment of union, of interaction with different cultures, interaction with different people, many languages. So everybody working together for a goal, one goal, right? And so this is very, very, this is impressive. So I never know a place like CERN. Also ICTP, I know ICTP, and ICTP is also a great place. It's a magic place, you see. And but which is the common, apart from science, apart from research in physics, and so in other areas too, the main characteristic of these places are the interaction, are the union of people working for a goal, yeah, towards a goal. And this is very important to me. And here in Brazil, having this experience, I try to improve, I try to support girls mainly, not only girls, but everybody that comes to me and needs some kind of instruction, some kind of, well, a word that can change their lives, their future, saying that it is worth to follow their dreams. So here in Brazil is very important because of our conditions, the society conditions, that it's not very good in many sense. So I am at your disposal for other questions that appear, and if you want to know something else.
Sure. Thank you very much for that introduction of the situation there. I know other countries which have similar situations around the world, and it's something that we can address the best we can as scientists. Well, let's move on. We have one more person joining us in our panel, and that is Jennifer Nikadyuba. Jennifer is a research fellow at California Institute of Technology, better known as Caltech, who's developing cutting-edge research methods in high-energy physics. She received her PhD at the University of Zurich in 2017, and afterwards spent 3 years as a senior research fellow at CERN. As a member of the CMS collaboration, she's produced several physics results that pushed forward the urgent quest of new physics and coordinated physics analysis groups. Her main interest is now focused on enabling new discoveries at the LHC and beyond with modern artificial intelligence methods applied at all stages of the data processing, from the real-time analysis on experimental hardware to the offline reconstruction. It's really nice to see the LHC and beyond, because for many of us, we might not see the and beyond yet, but I'm sure that you will. Jennifer, welcome. Please tell us a little bit about yourself and about your work.
Thank you, Steve, for this nice introduction. I'm super happy of being here. And yeah, as I said, so I spent the last few years focusing my research on the application of artificial intelligence technologies in particle physics. And I find this very exciting because I think we just started scratching the surface of like the huge potential that these technologies have in boosting our our fundamental research, right? From aiding us in discovering new particles, like dark matter candidates, as Katarina talked about, to actually even finding something that we haven't thought of. So, meaning we can even think about, we cannot think about something that it's much easier than what John's map can actually cover. So we can use these technologies to really enrich our knowledge about the universe. And we had several examples, for instance, during this conference of what we can do with that. And so what also is interesting is that so AI actually is something like artificial intelligence, something that is in our daily life, right? It's in your phone, it's in your car, it's in your Google search, and it's even in your bank account to make it safe. And so there was like a massive development of these new technologies outside what we're actually doing in fundamental research. And so the big challenge now, which is what I'm so interested in, is like to bring these massive developments that were in industry, like outside physics, like and bring them in our field and actually bring this much forward. And so because there is this, let's say, interplay, because we're borrowing actually from outside and bringing it here, what's very important is the very close collaboration with people from very different researchers from very different fields, and that's something that was also brought up before about like the collaboration, right? So it's not only about like collaborations among many different countries, but also it's collaboration between different backgrounds sometimes, and that's AI actually is bringing together these very heterogeneous. Say group of people, and then while let's say I'm mainly driven by curiosity, like discovering like something new, like some new laws about the universe, I also understand like the huge impact that that these technologies can have in our human life. And so when you work together with the industries, you actually work together to make innovations that to solve common challenges, but at the end you find out that in this work, we're actually bringing very big benefits to the human life as well, because AI is applied in many other things, not only in particle physics, right? So it's applied also in understanding like climate change effects to like diagnosing diseases or predict actually how diseases spread and this kind of thing. So I'm really proud of being part of this innovation. Thank you.
Very good. Thank you very much, Jennifer. It is you touched a couple of very important points there. That artificial intelligence, machine learning, these things are become extremely important for our field because it's very complex. The physics we do. If you look at the data that comes out of these detectors, it's not so easy to pick out the needles from the haystack. In fact, that's a very optimistic thing, a needle in a haystack. We have actually tens of thousands of haystacks with a needle in it. There's a lot of background in some of our events. It's very complex, very difficult to find. The other thing you touched on there, which I think is very important, is that, in doing the research, and John also mentioned this as well, in doing this research and developing methods and developing technologies, we provide a lot of things which are useful outside of our field. That just happens all the time. And one guy came up with this device for us to share information called the web. And I don't know, I hear that's going to catch on. I'm not sure I believe it, but I think the World Wide Web might make it sooner. Anyway, I think it's time for us to answer some questions. I was trying to look at the same time at the questions coming in, as a lot are getting upvoted. People should continue to do this. I'll do the best I can to keep up. I'm going to start with questions. There's one for Katarina, I think, but any of you can answer as well, which is people are fascinated by dark matter. I think everybody loves ice cream, so that works out well. And this question has a few parts to it. And so on one part, they're asking some very specific things. How do gravitation, this is from 1010 Nguyen. I think actually in this case, you don't pronounce the G, so Nguyen. How do Gravitational waves, neutrino, gamma ray, and antimatter detections help dark matter research. But the part of that question, the second part there, which I think is perhaps the easiest, the best one for us to answer here, which is how would the LHC know if the proton collisions produce dark matter? So maybe we can start with that. Maybe Katarina, you want to take a first stab at that, and then anybody else can join in.
So thanks for the question, because it's really an excellent question, and it's something that I didn't necessarily have time to go into the subtleties in the short talk. But the answer is that the LHC does not know if it's producing dark matter. It could be producing some other invisible particle. And that is why it's so important and so essential to have all the other different experiments to confirm it. So if you think about the WIMP case, where you have the LHC, direct detection and indirect detection all looking at the same kind of particle, then indirect detection and direct detection can discover the cosmological dark matter, so the dark matter that is actually in space. And then the LHC can complement that by telling you what is happening with the interaction, because we know what the initial state of this collision is. So I hope this is, and this is why it's so important to all talk to each other and have a common theory frameworks as well to get the results to be compared. I hope this answers the question, but I'm sure that there's others that have answers as well.
I think I might just simply add the simple fact. Maybe this was said, but maybe I missed it. I had this proton beam going through my ears here, so that might have affected. But what we would notice specifically, if you look actually at I think what is my left ear, you see a big wheel there. At that big wheel, that's part of our detector. Our detectors are symmetric; they go all the way around the beam, and so if we produce dark matter, there's a collision. We expect that all the tracks that we see going around that plane of that wheel, you don't see my hand all the time here, but everything in that plane should add up to roughly zero because of conservation of momentum, because the collisions come the other way. They come like this. There's my protons, and so you would see that there's just, we're missing some energy or missing some momentum in that. So that's what Katarina is referring to by the indirect, right? We would know something's missing. That's what we would know. We wouldn't be able to say, that's dark matter. We know something's missing. And if anyone wants to add to that, or that's my simple explanation. Steve's simple explanations.
Yeah, maybe one thing that I didn't mention before is that you can also say, I think this particle that I have, this invisible particle that I have detected is within this theory, and then check that it corresponds to that theory. That's another way of trying to determine from the LHC what you're seeing. But of course, you always want the explanation from the other experiments as well that actually can see cosmological dark matter.
Maybe there's one thing I could just add, because I like that Katarina mentioned the framework, the theoretical framework, and so Suchita would like this too. But it's maybe a difficult thing to understand that we lay down the whole evidence for dark matter is within a framework of understanding that includes the particle physics interactions of the Big Bang and includes our understanding of general relativity and how the universe develops. And it's often that you're finding things that don't fit that framework that really works. So you often know one experiment on its own will give you the golden bullet that this is a thing. Just like Vera Rubin's observations don't tell us what dark matter is. They just tell us there's something there that doesn't fit the framework. And that's a clue that you go and try and test it with other bits of the framework that you do know. And the LHC excels at testing one set of parts of that framework. Astrophysical observations and theoretical consistency and mathematical consistency are other tools that we try and use. And we're always doing these cross-checking consistency checks. It's very rare that some result is just suddenly, there's that eureka, that's something completely new. Because you probably knew there was something there that didn't fit your framework, and we try and adjust the frameworks to make them fit, and in the end, sometimes we just have to throw the framework away, or at least modify it fundamentally to accommodate the data.
Exactly. I see the blue hand of Patricia up. You want to make a comment?
Just complementing both your speeches about this question. So just the importance of statistics in all this environment, because now in LHC, so we work mainly with statistics, also with so the machine learning, deep learning to differentiate so signals of dark matter from others that can mimic, you see, its production. So the importance of statistics in high energy particle physics, it's a good point too.
Yeah, that's a very important point. Because there are other things which would leave nothing in part of our detector, such as neutrinos, but we know statistically from our models, as John said, in different frameworks, from our models, we know what to expect and see if there's something that we compare with something that's different from that. Okay, let me move on. I think we're going to come back to dark matter because there's seems to be a lot of interest in dark matter, but I'd like to move on a little bit. There's a question for Kate, and I will ask you. Let me find it here. It's specifically about the progress that you see. So the question is worded like this: Kate, within your outreach master classes, on your visits to various places, do you get excited as the politics gets better in some places, or depressed that things aren't moving fast enough? I guess the question in general is basically, are you seeing progress, or not?
Yeah, that's a good question. Yeah, we're seeing progress in a lot of countries, and it really does depend on who we're working with and the motivation of some of the leaders, if you like, the people in charge. And yeah, in some places it's super easy actually, and you can make progress very, very quickly when everybody's on board, because a lot of things in physics you don't necessarily need resources for, so you can make at least some initial progress. But yeah, you get a lot of stumbling blocks, especially when it comes to things like funding. Obviously, funding is always one of the big things we're spending a lot of time trying to search for and look for. And some places it's difficult to convince policymakers and leaders that this is an important thing to do for young people and for universities to be involved in physics. And that can be, well, yeah, it can be depressing if you like in the beginning, but at the end of the day, you're still working with these people who are super passionate and interested in physics, and we still work with them as best we can. So I think it's always an optimistic forward progress. It just depends on, some have more stumbling blocks than others.
Anybody else see anything differently on your travels around? I think you're doing much more traveling than the rest of us. Good to hear that there is progress. In some places, I think maybe it goes backwards, but it's.
Yeah, I wasn't going to mention the situation in London right now, but
yeah. I was thinking of my own home country too. So, but
I think Patty would like to comment as well.
Okay, go ahead.
Patty, we cannot hear you.
You're muted, Patricia.
I maybe I didn't understand. You asked about master classes, right?
I think it was referring to the work done to support students in developing countries.
It's in general, Patty, not specifically about master classes, but in general.
Okay.
Okay, so let me move on. There's a lot of good questions here. One which I think is pointed towards John, which I will just sort of paraphrase because I don't find it very quickly in this, but it was essentially about whether we're going up. They said in velocity. I think what they mean is going up in energy. For future accelerators, will we be going up in energy in the future? And I think in general, just to comment on what are the different ideas for new accelerators in the future.
Okay, so yes, so the thing that's most certain is the high luminosity that we will get from the next few years on the Large Hadron Collider. That's not directly an increase in energy, although actually it increases precision. So in some senses, it has in some processes, it has a very similar effect to going up in energy. But it's more about precision than energy reach, I would say. It allows, if you go back to the map, it allows us to do a better survey on a wider range of the map, but it doesn't extend our reach on the map very far. So we are thinking about the next step after that in terms of the energy frontier. And the number one priority at the moment actually is paradoxically not to go up in energy, but to step back and look at the Higgs boson more carefully. So colliding electrons and positrons has advantages in terms of precision over colliding protons. And there are a few proposals around to build what we call a Higgs factory. So the LHC did a kind of broad sweep and found the Higgs there. Now we know where the Higgs is. We can build a collider to specifically target it. And the Higgs is, we hope and think, a kind of a gateway to some of the unanswered questions of physics. No guarantees, again, that it is, but certainly there are a lot of unanswered questions that you can address by studying the Higgs more carefully. And that would be stage one of that future circular collider, for instance. That's one of the proposals. That's the one that's favored in Europe at the moment. But there is also a proposal to build a similar thing in Japan, a linear machine in Japan, for example. And then the second stage of that future circular collider would be to do the LHC again, only bigger and better. And that would really push us further out east. So the answer is, at the moment, it's about luminosity more than energy, but the plans that we're drawing up for the next step after that are about energy as well. And maybe it's also worth mentioning that the technologies that we would want to build those machines don't exist yet for some of them. So it's not just about digging a bigger tunnel and filling it with the same stuff that we filled the last one with. There's a lot of work to be done on high field magnets and on high temperature superconductivity and various sort of things which people at CERN and at national labs around the world are working with industry on, and with materials science and engineering, to try and make these things doable, because at the moment they're not doable. It's not just a matter of digging a big tunnel and writing a big check. We have to actually work out how to do them from a technological point of view as well.
That's nothing new to our field, right? I think that when we were...
No, that's the way we work. As I say, digging big tunnels is boring, right?
Yeah, exactly. We're always trying to do something, and I mean that's an important part of our field, right? Because we push the technology, right? We didn't know how we'd be able to make niobium titanium, come together and be flexible enough to be able to build the magnets that we built for the LHC. But we already had plans. It just had to be done, and we managed to do that. Now we're looking at niobium tin, I think, is what's being tested for.
That would be the low temperature superconductor, yeah. And then they're also looking at high temperature options. I think you missed my pun, Steve. I don't really think that digging tunnels is boring. It was a pun.
Yeah, I understand.
Sorry.
But yeah, I mean well, there's a lot of things that are up in the air. But the thing about this is that the projects, they're really long term, right? The ideas that have been put forward in our strategy are it's a 70-year plan. It's a long term. We have no idea what technologies will even be available later on in that, so we'll have to be able to adjust. And that's true in all aspects. I mean, nobody knew what a petabyte was when we started the LHC. We had never, we were going to get petabytes of data, and that word hadn't even been invented yet, if I recall, when we were first starting the planning, which was back in the 80s and 90s. So every aspect of this, we don't know. There were some technologies that are still being looked into, this idea of a muon collider, for example. Muons are the more massive sister of the electron. If you can manage to get a muon to live long enough and accelerate it, when you have a collision, it's a fundamental particle like electrons, you can go to very, very high energies and thus high masses, and that will produce more Higgs, for example. But that's quite tricky because muons don't live that long, right? Is that project still being considered, John?
Very much so. In fact, I mean, it's a higher risk technology. The ones I presented, if you like, are the sort of They're still quite high risk, but they're the lowest risk technologically speaking. But there is an international effort underway to look at whether muon colliders can be built. Also, you can use muons to get intense beams of neutrinos, so that there may be physics you can do on the way to a muon collider as well. There's also a very active program in plasma wave field research going on at CERN to try and get electrons to high energies more cheaply and quicker than we can at present. And plasma wave field technology and energy recovery linacs are also, there's a whole plethora of innovative accelerator ideas, but at some point you have to make them real and you have to put them into it. These are huge industrial scale construction projects. So it's not a matter of some bright people in a lab coming up with a great prototype. You've also got to industrialize it. You've got to make it so it can be mass produced and deliver on schedule and on budget, or as close to schedule and budget as you can manage. So it's the whole project engineering as well as the technology engineering is a challenge, to be honest. But yes, certainly muon technology, muon collider technologies, plasma wave field technologies, energy recovery linac technologies are all in the mix as well. Yes.
I'm gonna change topics. We have to jump around a bit. There's a lot of interest out there, and there was a question that was pointed to Jennifer, which is a challenging one. It's an interesting one for you. It comes from I hope I pronounce it correctly, Matuz Juriki, or Juriki, and Matuz asks, you mentioned that you use AI for physics research. To what extent, if at all, is elementary particle physics in return used for AI development?
Okay, yeah. Well, so how do we use AI in particle physics? Well, so you heard from John, for instance, that we are going to build more and more complex detector, which means that we're going to have much more and more complex data. So to make actually any sense of it, you need like some sophisticated algorithms, which you say, okay, I can handcraft them, but to handcraft them, then it's going to take you maybe, I don't know, like a lifetime. While instead we use AI because they can find a solution into that. And so let's say it's kind of a shortcut, and it actually works. And at the same time, so our data, like our particle physics data, are really, really custom, let's say, or like specific of our field. So to interpret them, we need like some technologies that are new with respect to what actually industry is doing for many other applications. So that's why, like, when you start collaborating with people outside physics, like so from industry, then you find, oh, look, what you're doing maybe can also be applied to what I'm doing. So I can give like one example, which is, for instance, like at the LHC, we have a big challenge, which is like running very complex AI algorithms in very, very short time. I'm talking about microseconds. And that's, it's really like, let's say custom of our problem, but not so much, because if you talk to people like developing algorithms for self-driving cars, AI technologies for self-driving cars, they do have like exactly the same time frame. So like just maybe not microseconds, we're talking about milliseconds, and that's still like really, really short. So in that case, like that's like one example of like application of like exchange of information, knowledge transfer between us and them. And indeed, we are collaborating, for instance, with companies developing self-driving cars, because like they have giant models that have to like run in very short time, and we also want to do the same. So they have some expertise, we have some other expertise, and then like you fuse them together.
Very good.
Hope this answers the question. That's just one example, but there can be like many others, and that's why we have also like a knowledge transfer at CERN, department at CERN, that actually makes us communicating.
Is that right? Do we have an expert here from knowledge transfer at CERN?
Yes.
and that's it's a typical story, I think. No.
Yes, it's a typical story. There is many examples of applications of the technologies that are connected to accelerators, detectors, computing, and not only technologies, but also human expertise associated with them that translate into positive impact on society in many different fields, like ranging from aerospace, safety, cultural heritage, and medicine. That's the big one. So just an example, there is a sensor from microelectronics developed at CERN. I don't know if you heard, Medipix, that has recently been used in medical imaging, allowing to perform the first ever 3D X-ray on a human. So there is many applications well, I'm speaking about CERN technologies, but in general, accelerators, detectors, computing, and
I think many people aren't aware of everything that's coming out of
yes,
our field and
that's
are
my job.
affecting them. And it's your job to make us aware of that. I mean, everything from our ability, as I mentioned, the World Wide Web, the touch pads that we have.
We're talking also about like simulation, for instance, like when you want to like simulate like big effects of like climate change or so, like you need like very sophisticated algorithms, and that's like something we have in common because we also simulate very complex data. And also, like, for instance, all the research that is done, for instance, in quantum computing as well, like we are doing that. They're doing that also in other fields, and that's like a very common ground.
Yeah, this is where we contribute, even in the financial sector, to that, for the good or bad. I don't know. Actually, I've found, I'm going to move on to another topic. We got a lot of different topics here. I'm really happy to have all these great questions pouring in. There was one there was a specific one for Patricia to answer. It's a little personal, but I think it's a good one. And they want to know, how can someone who has a PhD in particle physics phenomenology get a postdoctoral position in experimental particle physics? It's a great question. They didn't ask you how did someone who is a mathematics degree get a PhD in particle physics phenomenology, but I can understand that myself. My first degree is in mathematics. But yeah, can you tell us how you made that shift?
How I did it? Well, it was not that so hard, okay? Because mathematics give you a basic, so the language, yeah, we talk in physics. Then, after a few years, then I entered and I started to study electromagnetics, quantum mechanics. So my first contact with quantum mechanics was in my mathematical bachelor, in my mathematical undergraduation. You see, so my first contact, I was interested in physics since my mathematical undergraduation. Okay, so it was not so hard because I had a contact before. Then I developed all connection, so the connection with physics, because I had the language, so you see, and then I had to learn how to read the nature through physics. Okay, so more or less like that. Then I did so I did 1 year in the professional disciplines, so electromagnetics, quantum mechanics. Then I started officially my master in science. Okay, so it was not so hard. It was smooth. It's not so difficult.
Okay, so yeah, I mean, I think your lesson that you bring to a lot of people, and you're a great role model in many ways, but is that you can change your mind. You can go into different fields.
You can change. I changed it a lot because I changed it from mathematics, pure mathematics, to physics. Then in my master, I did physics applied to medicine. I worked in proton therapy, so application of physics in Hadron therapy. So therapy, radiation therapy with heavy particles, called proton therapy. And then after in my PhD, I increased the the proton energy and became a particle physicist. So it's so I changed a lot. And so you don't need to fear changes. It's very interesting. It's very good for your brain. You see, you make
good lesson.
connections. Yeah,
a good lesson for everyone. It's appreciated. Okay, we have a challenging one, which I'm afraid John and I are going to have to try to address, but maybe we can get others to help out. and this is one Rachel's asking, and it's asked actually in a couple different ways, but I think it's the same sort of thing. I think I saw it down below too, but let me get to it here. So it seems that prominent quote leaders and members of public are fed up with quote experts as scientists. How can we sway public opinion so that people regain faith? Who would like to address that?
I'll have a go. You mentioned it, Yvonne. It's not about faith, is the bottom line. You've got to give people the information. So I don't think we should be in the business of trying to sway public opinion. I don't think we should be in the business of encouraging people to have faith in us. What we should be doing is presenting what we do and why we do it and how we do it as clearly and as enthusiastically and as honestly as possible. And that's us as scientists. Now, us as citizens, we should be very politically engaged. I think we can't afford to sit in an ivory tower is a cliche I'm trying to avoid, but I failed. We can't afford to sit in our cozy little particle physics world assuming society will just keep going doing the things that interest us, and society will function to keep us supplied with the things we need to do that. So I'm drawing a distinction between us as citizens of the world and us as scientists. But us as scientists, we should not be trying to sway people's opinion. We should not be trying to instill faith. We should be trying to put facts out there as clearly and enthusiastically and with all the clarity we can muster. And then as citizens, we should be arguing for what we believe is right.
Very good point. Very well said. I see this issue in the news all the time, and I do cringe when I see this word "believe" put up all the time. How do you believe? And I was asked this by some students. Actually, I gave a talk to some very brilliant students in Australia in November. We had a conference down there, and I was asked what do I believe about climate change, for example, and I was maybe a little harsh on my answer, but my response is that it doesn't matter what I believe. There's data, there is truth, there's reality. All we do is we measure data. We can take temperature of the planet and we can report that, and that's what scientists do. I saw once an interesting thing when the Higgs mass was revealed. There was a lot of discussion about it. It was just very, the Higgs mass had an important role. If it's light, that might mean something, one thing, that there's other particles out there. If it's heavy, it means one thing. And there was some report discussion that, this means that it could mean that we're in an unstable universe. This was one of the postulates put out there by you brilliant theorists. Maybe Suchita will comment on that, but it was put out there. And they said, look at what they've done. Look what these scientists have done. They've made the universe unstable. It's much like a doctor coming and telling you, you're sick, and then you blaming the doctor. We're just there to find truth, to measure what we can, and to reveal it as honestly as we can. And that's, I think, the importance that Kate brings with this diversity, is that if you have many, many people from all over the planet using their different ideas and different ways of looking at things to come together to look at things, and eventually they see, they look up the sky and they say it's blue, and somebody else says it's blue, and you eventually have an objective opinion that the sky is blue. Eventually, when we're all on board and we've done all of the systematics and we've looked at things, it's very hard to make a paper, but by having this diversity, you have strength, and you're able to say that your measurements, here's our measurement, here's a paper that we produced, and we publish it, and that's a little bit of the truth, and that's all we can do. So I totally agree with what John said there. Maybe someone wants to disagree with him, or someone has another opinion.
Yeah,
any hands? Go ahead, Kate.
Yeah, I was just going to add. Also, like the LHC experiments release their data publicly, so I think that's a nice way for people to engage in the work that we're doing. And the experiments, they give step-by-step instructions and help people to know how to look for the, Higgs themselves. So they can understand what it is that we're doing in our papers and our experiments. And it is publicly available. So maybe, anyone could find a new particle by sifting through the paper. So I think that's, given that the LHC, they release this data publicly, that helps people realize that it's not behind some, some barrier or in some ivory tower. It's really, available to everybody.
Very good point. I saw Suchita's blue hand up first, John. Let's let her go, and then we'll come to you.
Sorry, John. No, I just wanted to add to all this discussion. Right? So I think one very important aspect of the story is also science communication, is that we need to be able to tell people what is it that we are doing and on what principles all that we are doing is motivated. Because at the end of the day, scientists are not 100% all knowledgeable people. It's a journey that we are on. Sometimes the conclusions that we draw may change over time because we know more about stuff. But fundamentally, the principles over which the scientists work are well-founded, and they have some very strong basis. So there's I think there is an important aspect of communicating that over, that there's a side of sticking to principles and having a well-defined framework on which science in general works, and scientists adhere to that.
Very good point. John, you want to add to that?
I just, well, it was kind of related to, I wanted to add a rider to what I said at the beginning, which is that the truth is actually political in the end sometimes. So there are cultures and areas where if you actually do report the data accurately, you will be persecuted for it, or at least very least your career will not thrive because of it. And when when society ignores the best evidence we have about things, and you can fill in your crisis of choice at this point, but when society ignores the best evidence we have about what is happening in the world around us and how to affect it, damage is done. And I think one of our jobs as scientists is to minimize that damage as well. So I'm qualifying my statement about trying to make science unpolitical. In the end, actually, the truth is political, but it's not about instilling faith in scientists. It's about presenting the truth.
Sure. Yeah, no, I completely agree with you there. I think also what I think would help is for us to reveal as much as we can, and we do this a lot. Everyone here, obviously, we're engaged. We'd like to do public engagement, but just to reveal the difficult process that we go through to publish, to actually say something, just to publish a paper is a long, difficult process where everybody in our collaboration makes comments, and we have to, and we actually, when we have a result, especially a new result, we doubt it ourselves. So it's a very long, hard process to be sure that what we put on paper and put out there is as close as we know the truth. And I think CMS just passed us. They did this 1,000 times. They have 1,000 publications that they did, and we're not far behind that, 950 or something. We have a lot of publications ourselves. But these were hard to do. And the important point is that, none of us has a motivation to lie. If we're caught lying in one of these, it's the end of our career. We're done. We're out of there. We do not lie. It's just a very bad thing in our career or anything. And it will be found. It will be found. You can't. It's just, the data's there, and you put it out there as much as you can. And we're not afraid to change. As Suchita said, we will go in different directions depending on which way the data take us. And we'll go to a conference like ICHEP and proudly give a presentation about how we failed in a certain thing. we will do that because that's our part of our field. We will say, look, we tried this method, we tried this, and it didn't work. And that's marked down as great. That's excellent. They tried this, and now we don't have to go there. And and I think that as citizens, we should accept that from politicians more. Politicians who change their minds based on new evidence should be valued. It shouldn't be that, oh, they are wishy-washy, they're changing their mind. It's a valuable thing for someone who bases their decisions on science. And so I agree, we need to be engaged, to watch what our politicians are doing, to reward them, and congratulate them, and vote for them when they are following science. And one thing that was mentioned at the very beginning of our conference, we had a guest star open our conference, Peter Gabriel, and I think that his comment was very very important there about the fact that we have to try to be more engaged, and more scientists should actually go out into politics. We're kind of scared of that world a little bit, but they tend to do fairly well. It's a different game, but we do need more of us getting into politics. I would agree with that. Any other comments on this? Was the topper question. It's hard to top this, but we do have enough time to do one more, and I think it's one that maybe we can all talk. We sort of touched on it here, but I think it's one of my favorites from in here, and which is simply, how does particle physics benefit humanity? So everybody, I think everyone should have a chance to give a word on this. Who would like to start on that? They're not all jumping. I don't see a lot of blue hands. Okay, there's a brave soul. Patricia, please go ahead.
Well,
Patricia, yeah.
There are two sides, huh? The philosophical side. So we need to know where we came from, right? So we are dealing with the components, the constituents of matter. We are matter, and we need to understand why we are here, what is going on. So a curiosity, if you have a minimum of curiosity in your life, so you will search for questions. So this is the philosophical part. You say this is strong philosophical part that comes from forever, since the ages, so stone ages. Where are we from, and what we are? Okay, so this is the philosophical. Apart from that, we have the technological part, right? So all improvements, we are here talking with you because of science. Web was built at CERN because our needs to communicate, okay? When you go to a medical to make some image diagnostics or magnetic resonance, you deal with detectors, you deal with radioactivity. So it's everything, it's merged in science. And I can say that particle physics, nuclear physics, and high energy nuclear physics, okay? So particle physics is one of the main, because we work all together, okay? It's none more important than other, okay? And so this is the important, what particle physics bring to humanity, everything. So we can talk now because of web. It was developed in a particle physics laboratory first. Okay?
Very good.
Many others, so others can comment, but this is my point of view.
Thank you very much, Patricia.
Go ahead.
Very good points. I think Kate was the next.
I think Patricia covered quite a lot very well, actually, but I want to probably reinforce her first point, that I think one of the key benefits of particle physics is that as a society, as a human race, we're able to build these giant machines and really understand what happened a tiny amount of time after, I mean, a tiny amount of a second after the Big Bang, and gain an understanding of the universe, of space-time, of the fundamental forces and particles. And I think that's super incredible. And it's an inspiration to young people and people all over the world. And it also brings us together as, you know, as a human race. It's everybody's endeavor. It's everybody's, it's to everybody's benefit to learn about these things. So I think I really like the kind of inspirational side of it, of, you know, learning. You know, it's not about necessarily economy or bettering ourselves. It's really just about our innate wish for knowledge together.
Very, very, very good point. Thank you, Kate. I think John was next.
Yeah, I'll be brief because I think I sort of alluded to this in my talk, but I completely agree with what Patricia and Kate have said. I think the main benefit, the unique benefit really of particle physics, is the scale of the questions it addresses. But to be more kind of prosaic, the actual economic benefit is the people. And we've seen this time and time again. Every time we do a study in the UK or Europe or globally as to what the benefits are, the benefit, for some mysterious reason, let's pretend you don't care about the deep questions, you don't care about particle physics, you don't care where we came from, you just want better gadgets, or you want an economy that grows faster. For some strange reason that you don't understand, lots and lots of people are motivated to do particle physics and to push themselves against this technology, to work in these collaborations. And most of them do not stay in particle physics. Most of them go and do other cool things that make the economy hum. And that, from a prosaic point of view, it's that's the real benefit to a society. That's why people want particle physics labs in their regions. However, that doesn't work without everything that was just said about the big questions, because it's those big questions that make people come and do this stuff.
Exactly, exactly. Suchita, do you want to add to that?
Yeah, so exactly. Again, going to the questions of curiosity-driven exploration of science, right? So one of the things that I always keep telling my students is, it doesn't matter if you stay in physics or not. At the end of the day, it's more important to stay curious for the rest of your life, because that's what really would drive your development in terms of understanding what is out there, how to make it better, or how does it help me personally in my own life. So that's one aspect of the story. The other aspect that I find, which doing physics and science and particle physics in particular has taught at least me, are very personal skills like self-discipline. I work on several projects at the same time, several aspects of theories at the same time. And in order to manage all that, I had to be very methodical, very disciplined, and very careful about how I manage things. And there is that aspect of the story, which are very personal development of skills that are useful, not only to your day-to-day physics life or day-to-day research life, but also to anything else that you do, business management, just your day-to-day lifestyle management. And that's also a very useful kind of a thing. So there is that.
It's excellent training, excellent training. Jennifer, would you like to add to this?
Yeah, I just wanted to add that, I mean, I agree with Kate, like that curiosity is probably like what drives us very deeply. But indeed, like there was a talk in the outreach part of ICHEP last week, and about like two types of students, right? The type that are just curious about things, and the type that instead are really, really devoted to some application, right? Some application that actually it's very tailored to maybe helping human lives and so on. So that's why like it's important like for us to like bring always forward like these two aspects of things. Yeah. And yeah, so I think indeed, I mean, there is like, I mean, like you can like start studying particle physics and then decide that actually, you find out like this application, it's what interests you most. Yeah. Mm-hmm.
Yeah, it's sort of like John and Suchi just said. It's a training machine. What comes out of these things are PhD, and that's fantastic. Katarina, I'm not going to let you off the hook. The sun is taking a really long time to set behind you. I'm not sure where you're at, but
Sweden.
Oh, that's true. It's probably could be real. Would you like to add? Do you have a comment you can make here?
I think everything that needed to be said had been said. The only addition, and to drive the point even more, is that we ask questions that no one has ever asked before. And in order to reach the answers to these questions, we need to develop and invent technologies that no one's invented before. There will be a use for them. It's like that joke that said, I think it was you can invent any tax earner and any taxpayer. And you say, Mr. Developer of electricity, what is the use of your invention right now when electricity was just brought forward? And the inventor says, well, wait until you can tax it. So this is a different side of the story, but the fact that we ask such big questions and we need to have such big answers, and we need to move mountains to get to those answers in terms of both the intellectual thinking and theories and in terms of experiments, comes back to society eventually, also with the artificial intelligence and all the things that we see, that there's a continuous exchange. So this, I think, is a benefit of particle physics.
That's a very, very good point. I see Marzena has her hand up too.
Yes, so I basically wanted to say what Katarina said, because we discussed the curiosity and I've been for a long time among physicists, working with physicists, and it's beautiful that we can discover new things and rewrite textbooks. But it's also beautiful that at the same time we can push technologies forward, and we can provide new solutions to some technical world problems. So that's beautiful that we can in fact connect all three sides. So curiosity, people that we train and they go and work in other domains, and technologies that can be reused in other domains. So that these are the three aspects that are definitely connected with the motivation behind doing high energy physics and seeing the benefits in society.
Very good point. Very good point. I think we're going to have to close. I want to make sure that everybody realizes the LHC is off. And so neither Marzena nor I or Patricia are in danger of having beams go through our heads. So we're safe here. I'll add, since I made everybody else make a comment, I can add my comment on the same subject. My personal opinion is that we don't have a choice to be realistic. Human beings, it's in our DNA, and you're not going to stop us. We're going to try to figure out the universe. We're going to try to figure out what's going on, and it's essential. We have to eat, we have to get shelter, we have to make babies. We also have to examine the world around us and figure it out, and then pass that information on, because it will be used by future generations. It's just the way it goes. I was once asked, as it was 3 years after the discovery of the Higgs boson, and it was I'm not going to say her name because I don't want to be fair, but she's a brilliant journalist who asked me this question, and she said, "Okay, so you found it 3 years ago. Now what have we got for it?" And that's a very, very good question to ask. We deserve to have that question asked to us all the time. We're using the public's money, and we deserve to tell the public what we find. That's the whole point of this, is to seek and then to report to the public what we found. I had to answer her that I'm sorry. I don't yet have a Higgsmobile. I don't have something I can give you. But if you come back and ask my great-great-grandchild, I will guarantee they will be able to tell you what they've got because of the discovery of the Higgs boson. It's just the nature of our field. It's long-term, and we have to do this. We have no choice. That's just my own opinion. Anyway, I want to thank everybody for being here. It's been great to be with all these brilliant minds. I think Kate had to leave us because she's a very important person and had a dinner to go to. So thank you, Kate, for having joined us. Maybe she'll see the recording later. Also, many thanks to our other speakers, so Katarina and John for having given very nice presentations as well. And also our panelists who were fantastic. I'm glad to have met all of you. And I hope to see you again when one day we're back in a normal world. So thank you, Suchita, Patricia, and Jennifer for being with us. Many, many thanks to my co-host, Marzena, for helping to put this all together. It's really appreciated. Wojtek's listening in. You're not out of this yet. Wojtek did a lot of work for the organization of the entire conference of ICHEP. I don't know if you want to, if you're there and you can show us your face, Wojtek.
Hi. Yes, of course. Yes,
there we are. Thank you so much. We really appreciate everything you've done. He's helped put together this whole program for the entire conference and all the public activities that went on as well. I hope that everybody had a chance to see Connie Potter's Big Bang stage, which happened. This was actually the final event of the Big Bang stage, although there's some more events tomorrow.
Indeed. There's going to be the Kaleidoscope music by Larry Lee. It's pre-recorded, you can watch it on YouTube, but it's going to be live in the Cross Club here in Prague, as it was originally planned. So originally we planned the ICHEP participants would come and listen to his music, play it on an oscilloscope. So we are inviting people from Prague.
And we had a taste of that at the very beginning. Larry Lee is this amazing physicist who makes music with oscilloscopes, and it's be something to watch. And I'm really sad that we're not in Prague. I happen to love the city's event. Beautiful, beautiful city, and it has great beer too, just so you know. But I really love the place. And we're going to be back in the ICHEP conference happens every 2 years. So in 4 years, we're going to come back to
Prague, hopefully. Yep. So
we will all be healthy by then. No more pandemic. Let's just hope for that. I also want to thank Mirabe, who's been working hard putting captions up, and I really feel sorry for her when I speak because I just, my words just go right together. But she's been working since early this morning. I don't know if we have a chance to see you, Mirabe. If you're still there you are. Hello. Thank you so much. It's not many people can go through a physics conference and to type down. I know that I couldn't possibly do that. So thank you so much for your help. We're trying the best we can to be as inclusive as possible, and we know that some people have hearing difficulties, and so that's what we could do to try to help out there. So again, thank you, everybody. And I should also mention Zdenek, of course, the big boss who organized the entire conference, and Zdenek Dolezal. And you mentioned Jaroslav Dilchik. Did I say it right?
Definitely. Jaroslav Dilchik was the coordinator of the outreach program at ICHEP. And then let me also say Martin Rybář, Connie Potter, Steve Goldfarb.
Oh, thanks. It was an absolute pleasure. It was a lot of fun to do. And thank you to the audience for sitting through all this. So we hope that we answered as many questions as we could. There were a lot of really good questions out there. So everybody, stay home, stay safe, stay healthy, and keep following what goes on in science, because science is the best, right? So take care, and thank you again. Thank you, everybody, and have a good evening.
Bye, everyone.
Thank you very much.